Welcome to the 21st class meeting of EECE341, Introduction to Communication Systems. Sorry about this recorded class meeting. I have my personal affair to do some other work on our class meeting hour. So I sent you an email that this recorded class meeting will be uploaded by Tuesday, 9:30 a.m., but I'm going to upload it by Monday morning. So this is Sunday night, actually, 10:25. Okay, so here goes some announcements as usual. So the first one is that the homework 21 and 22 will be assigned as usual, and due is, of course, on Monday, 9:30 a.m. That is just before the start of the class meeting. And on next Monday, not next week, this week is confusing, but anyway, on November 25th, we will have quiz number 2. So be well prepared for the quiz. Let me emphasize about the voluntary project because today I'm showing you the histogram and your conversion graph for your rho score in the midterm and z-score in the midterm. So for example, the students who got around 70 something point got z-score around 2.5, so which means that the students has the score around 2.5 standard deviation from the mean score. So here the student is. And once I told you that if student's z-score is above 2, he's an amazing guy. So this student, I know the student's name. I hope I can send you an email after the final exam. So good luck. I will really encourage you to think big for your future. Also, the students got amazing score around more than 1.5 is also very, very high, extremely high. It's kind of one student out of 5 years, something like that. So these students also got amazing, showed amazing performance. Also, these two students are excellent students, and I really appreciate that the students studied very hard. Unfortunately, there are around 3 students who has very, very poor score, especially the student who got around less than 1.5 sigma. I strongly recommend the student to drop this course. According to my experience, it's almost impossible to recover this poor score in the midterm until the final exam, even though he or she does voluntary project. I'm yeah, it's just past statistics. However, statistics has some good reasons why this occurs again and again. So yeah, if he or she believe the student want a meeting with me, then send me an email. Also, these 2 students got less than 1 sigma, so they are around here. Yeah, study hard. This course requires a lot of analytical skill, and I told you that be well prepared. Otherwise, this poor performance may be shown. Anyway, so for other students around here, now probably you are very interested in a voluntary project. So as I repeatedly told you, you need to confirm with me your project topic. And this topic must be approved by myself before you take the final exam. And my confirmation email you must obtain. Topics must be related to this course. some other topic is not well accepted. Presentation, PowerPoint, or PDF file, and presentation video in MP4 or file format of length 20 more than 20 minutes must be submitted. And you don't need to send me this huge file. You may use Postec webmail, where you may just simply attach the link to download, for me to download your file. If your voluntary project is related to programming, then you also provide me source code in MATLAB and Python, which are preferred, but not necessary. No reuse, no double use, no triple use is allowed. So that is actually cheating and is very severely punished. So be careful. And due of this voluntary project is December 26th, 9 a.m. So you must hurry, otherwise you have to spend Christmas Eve and Christmas Day to do this final project to save your grade. If you pass, around 80% who submit a voluntary project passes. So if you pass, your grade is one click up. For example, you are supposed to get, for example, F, and does your project very satisfactorily, then your score will be turned to D minus. And you may say that F to D minus does not mean anything, but for some students, I have found that they really can graduate, could graduate, and to be very successful after the graduation. So think about doing this voluntary project, and this is the first step. You have my approval on your topic. So let me show you this midterm result again. So this is the histogram in terms of the Z-score, and you have your raw score in your graded booklet. So you find your score and find the Z-score, and then feel how you perform. Since this is absolutely relative score, I may put, for example, A plus here, but no A, zero, A minus. It's up to me. I usually have my own measure how to assess your performance in the exam. But so far, what I have felt is that this bias to the left is very look bad, and I'm actually quite disappointed about the majority of your performance in the midterm exam. So I strongly encourage you to study harder for you to really grasp the essence of this course. Okay, so probably from this week, you will be given a chance to see the classes offered next semester, and these are companion courses related to communications and networks. So if you have any question, you also may contact me, even though I do not teach all of these courses. I will just teach this introduction to digital signal processing. And during the weekend, I've thought about the emphasis, and I have changed my mind a lot. So I'm going to emphasize doing Python or Python programming to do some digital signal processing. So I may provide you MATLAB examples, and you write your Python code, something like that, to do digital signal processing. You will have some hands-on experience, and you will really grow in this area. Okay, here goes the messages from me, and simplify and visualize existence and uniqueness, why not, and what if. And I've also remembered that I emphasized the commonality of great inventions from very famous patents. and they have commonality that scarce resource is replaced by abundant resource, and also for arithmetic operations gives us some ideas. Sometimes you add two interesting things. For example, hey, what about cell phone plus uh, computer plus touch screen? That is the smartphone. Sometimes you remove something that thought necessary, but that gives a lot of new advantage. For example, I emphasize that the initial Heinrich Hertz generation of electromagnetic wave heavily relied on what this is for the receiver, but the spark gap. And they had the spark gap receiver counterpart, which was spark gap transmitter. And spark gap once believed to be necessary component in radio communication, but people started to realize that's not the essence or necessity, and they removed that, and your cell phone does no longer have spark gaps. So they removed some unnecessary parts. That was huge advance. And sometimes you have not only single one, you may have abundant ones. Like, for example, your cell phone now has inside of it, it has many antennas, so that wherever you grip, your antenna is not blinded by your hands, something like that. Sometimes, as our big trees do that, they, in order to pump up the water, they have very small pipes. So instead of having this thick single pipe, they have a same sectional area, but many small pipes, and which automatically pumps up the water up to the 100-meter height tree, something like that. So this plus minus multiply and divide is also important message from me. Okay, so was there anything to correct? It seems I couldn't find, fortunately. So here goes the course overview. I hope we can finish this chapter for today and move to digital communication part, which are very exciting topic. And as I told you, I'm not going to cover many of these parts because I didn't, and also our department didn't put the mathematics for electrical engineering students A, which related to probability and random processes as the prerequisite of this course. It was not prerequisite. So I'm not going to talk too much about this, but in your digital communications, so this course that will be offered next semester, spring 25, this 302 is a prerequisite. That's what I remember. So if you want to take that course, digital communication, be prepared to have this one fully well reviewed or reminded in your brain. Okay, so I'm going to be very fast because it's almost three quarters of the semester already. Okay, here goes the review of the last class meeting. So we studied the receiver part of angle modulation. So here is the transmitter, and here is a receiver, and radio wave propagates through space. And by the way, I'm going to talk about this propagation channel, radio propagation channel, a little bit today, so that you understand why we talked about bandpass limiter last time. But anyway, so suppose that this transmitted signal is angle modulated signal or phase modulated or frequency modulated signal. So the signal applied to the antenna can be well modeled as a real valued bandpass signal, especially with a fixed amplitude, and you have carrier with nominal carrier frequency FC, and here goes the instantaneous phase deviation. Sometimes this phase is some affine function of message. In this case, this is phase modulated signal, and sometimes the derivative, which is related to the instantaneous frequency. Actually, since this is nominal frequency, this is instantaneous frequency plus, sorry about that. Yeah, so this is the instantaneous phase deviation. So this is instantaneous frequency deviation. That may be some affine function or linear function of the message. So this is PM and this is FM. And now this such a signal is transmitted over the air and received by a receive antenna. And what do we do to extract the message from the received signal? And this received signal may not be well modeled as a just attenuated and delayed version of the transmitted signal, as I will tell you today at the end of today's class meeting. But as I emphasized, simplification is the key to understand the essence and have some good experience about solving the simplified problem. So the first assumption is that this is some attenuated and delayed version. And we may simply say that the attenuation is one, which is that no attenuation occurs, and delay is also zero for simplicity. So as I told you again and again, many of these communication-related textbooks utilizes this simplification technique, because otherwise you cannot just understand the problem because it's too complicated. So think about the case where you have the transmitted signal appearing at the output of the received antenna. Of course, as I repeatedly told you, at this point, actually, the signal cannot be modeled as a real value bandpass signal. Actually, still here, it is an RF signal that propagates through the RF cable. However, we can model it as a real value time function, which are all real valued bandpass signals. Anyway, so we have some constant times cosine 2 pi fct plus phi of t. Now, the idea is simple. We want to make a receiver. By the way, as you've seen in the your homeworks, the early terminology in radio communication about this receiver was detector. So they said detector instead of receiver. And especially for angle modulation, they used discriminator in some historical reasons. So here, even though we have frequency modulation FM discriminator, you may just replace it as FM receiver. So the idea is simple. Let's differentiate the angle modulated signal. And as you've seen in high school math, if we differentiate with respect to t, first you have a and sine 2 pi fct plus phi of t, and cosine differentiated becomes negative sine. And then you differentiate this one. So you have d dt of 2 pi fct plus phi of t. So, what happens? We have this 2 pi fc plus the phi of t dt negative a sine 2 pi fct plus phi of t. Now, the idea is simple. You have envelope detector. Then what happens? And many textbooks says that this is the envelope. And if this is frequency modulated signal, you have DC block circuit, and that removes this part, and you have something proportional to the derivative of the instantaneous phase deviation. So if your signal was FM signal, you have your signal back, and if your signal was phase modulated signal, then what you need to do is that you put an integrator so that you recover the phase. The problem is that it's very hard to see whether the signal here after envelope detection becomes your desired signal. So as I emphasized again and again, let's see that this is a transmitted signal and received signal are both real valued bandpass signals. So let's use complex envelope notation. So what does that mean? So here you rewrite the signal as 8 times e to the j b of t e to the j 2 pi fct. Your conversion from this signal to that signal must be instant. That is what I want you to do after you taking this course, because as a communication engineering professor of experience more than now 30 years, I dearly believe this is the key. Got it? So similarly, what you can do is that after differentiation, you have the very similar notation. The difference is that now you have signed something, so you must remember the Euler's identity. So something like xi of t plus j xq of t e to the j 2 pi fct real part gives you xi of t cosine minus xq of t sine. So here is your minus or negative sign. So your real part is 0, and your imaginary part becomes what? Your imaginary part becomes this one, so which is 2 pi fct plus dv dt, and you have that one, e to the j 2 pi fct plus v of t. And you have one more trick, which takes this part out. So you have real part of j 2 pi fct, sorry, 2 pi fc, fct pi fc plus dv dt e to the j v of t e to the j pi fct. So actually, this becomes the complex envelope of your differentiator. Why do we convert this real valued bandpass signal in this form? Because envelope detector actually does this mathematical operation. What kind of mathematical operation? It actually it does not have intelligence usually, but it mathematically converts real valued bandpass signal in this form. And then it takes the envelope and then takes the modulus of it, absolute value of it. So what do we have here? Actually, we have here the absolute value of this one. But interestingly, absolute of j equals 1, absolute value of e to the j phi of t equals 1. So we have here absolute value of 2 pi fc plus d phi of t dt. And if this is an FM signal, what do we have? We have some FM M of t. So here, the signal is what? Proportional to FC plus this one. So suppose FC is greater than that one, then in that case, what we have is that we have plus FC, and this one runs here. So even after we take the absolute value, it's still the same as 2 pi fc plus 1 over 2 pi kf m of t. So if we DC block, then this goes away, and we have here the something that is proportional to the message. So you must have this very well in your mind. So whenever you are given a real value bandpass signal, you have to be find out this complex envelope form. And also whenever you have a differentiated real value bandpass signal, you also must be able to find this complex envelope like this. And envelope detector does this complicated mathematical operation. Of course, as I repeatedly told you throughout this course, there are two buildings of electrical engineering. On this right side building, the persons like me does theory. So we think about some mathematical operations that can result in very good things. For example, if an electrical system can differentiate the received FM signal and convert it to a real part of complex envelope of e to times e to the j 2 pi fct, and we have some circuit or computer or anything, smartphone that can take the uh, absolute value or modulus of the complex envelope. And if the modulus of the complex envelope does not, it's like in AEM, the no under modulation occurs, then we can extract the message signal by differentiating the received signal and finding the envelope of the signal and possibly this block. Got it. So we design on the right side building this mathematical operation we find, and what does this the guys in the left side building? They find a clever way to implement that idea using inanimate, in Korean 무생물의 생명 없는 circuits, wires, capacitors, OPMs, sometimes smartphones, something like that. So it's very, very amazing. Anyway, so that was the idea. The problem is that why we have bandpass limiter in front of this differentiator. So here goes the bandpass filter, and here goes the limiter, and here's the low noise amp, something like that. So why this part is observed in the practical FM receiver? Why? And I just told you that the received signal may not be this simple ideal signal that is the attenuated and delayed version of the transmitted FM signal. It may have some strange component like G of T. So your signal is amplitude distorted signal, and I didn't explain why. And today I'm going to tell you what kind of phenomenon introduces this amplitude distortion. But I will defer it to the end of this today's class meeting. Anyway, so bandpass limiter does what actually clips the received signal. So the idea is like this. Suppose you have some very fast varying signal, but you have some threshold so that you may clip the signal. And in this case, this some parts of the signal are not clipped, but suppose all the signals are above the this clipping threshold. Then what happens? Your signal becomes something like this. So its amplitude does not change. It's limited. Now, what's going on in the frequency domain? Usually, in a short period, this looks like a periodic signal. So it's not but a complete sinusoidal signal, which means that it's periodic but not sinusoidal, which means according to the Fourier series, we have a lot of harmonics. So in the frequency domain, we have something around here and some high order terms. Depending on the shape, sometimes we have only odd multiples of the carrier frequency. So if we have a bandpass filter that filters around this one, actually the signal becomes something like this. So zero crossing points are almost preserved. I'm not saying that it's preserved, but so we have smooth curve. Sometimes, of course, it goes up, but this amplitude distortion variation is much reduced. So you have almost non amplitude varying distorted signal back from this limiter followed by bandpass filter. So be careful. I'm not saying that these zero crossing points are perfectly preserved after the bandpass filter. I'm not saying that after the filter, the signal is constant envelope, but it's approximately constant envelope. So your idea of having differentiator followed by envelope detector and DC block works very, very good to extract the message signal from your FM signal. Got it? So that's why we have bandpass limit. After spending a lot of time to explain this idea of using differentiator and followed by envelope detector and DC block circuit, and the reason why we may remove the amplitude distortion in the non-ideal received FM signal using a bandpass limiter, I talked about the PLLs. That has been and once was an essential component in digital communication receivers. And I emphasized about the Costas loop or Costas PLL or Costas receiver, EI. But as I told you, I'm not the guy on this left side building. So my emphasis is on this one. Similar to the feedback loop that makes wonderful things for operational amplifiers. The feedback loop appearing in voltage controlled oscillator or PLLs really makes everything very, very interesting. So please remember that. Okay, so I spent around 30 minutes as usual to review the last class meeting material, and I'm going to give you a preview of today's material. So we are going to focus on interference in angle modulation, especially for FM modulation. And we will see why people put pre-emphasis filter in the FM transmitter and the emphasis filter in FM receiver. So you not only need to understand this basic reception idea, frequency modulation, FM discriminator using differentiator with envelope detector, and also use of bandpass limiter, you also have to understand why people put pre-emphasis filter and de-emphasis filter in the transmitter and receiver of FM radio, respectively. After talking about that, I will talk about this interesting thing. So if you tune to AM radio station, your sound is monophonic, which means that we simply say mono. So right speaker and left speaker gives us same signal. But if you tune to FM, we may hear some stereophonic signal, stereo sound. And some people who didn't major in electrical and especially communication engineering say that FM means stereo, AM means mono, and that is totally absurd actually. So I will talk about why FM can carry how FM modulated signal can carry stereophonic signal. And the last topic in the according to our textbook and the handout made by Professor Kyung-Chul Yang is quadrature multiplexing, and that is also related to the analog form quadrature amplitude modulation. And so after I talk about this one, I will talk about multipath channel. So as I told you, why bandpass limiter is needed in the FM receiver is because your received signal may have amplitude distortion. And the last thing, this part explains how amplitude distortion occurs in the radio received signal. Okay, so here goes the first topic, interference in angle modulation. And the first subject is that the interference is the case where interference is weak, and then we will see when the interference is strong. But yeah, this is a good simplification, but I believe I can combine them together and explain at once. So here goes our model. So received signal is assumed that AC times cosine 2 pi FCT plus AI cosine 2 pi FC plus Fi of t. Actually, there is no message. So this is the desired signal. So this is the desired signal. And this is the interference. And the desired signal has no phase deviation. So actually, you may regard the case where message signal is silenced. So of course, when we do radio broadcasting, sometimes we don't speak, right? So in that case, the receiver ideally must generate no signal, zero signal. So after the demodulation, the signal must be zero. However, due to this interference that has, of course, no message, but have some frequency offset from our desired carrier. So Fi is the interference frequency offset. Then what will be the effect of this non-zero Fi? Got it? So consider this case. Suppose Fi equals 0. What will happen at our FM receiver? No signal, right? Because you have same FC, so AC plus AI cosine 2 pi FCT would be the received signal. And since there is no time varying phase deviation, your FM receiver will generate silence signal, right? So with non-zero Fi, we will see what will be. So supposedly, this period, short time period, must be silence period. However, due to the presence of interference with small frequency offset from our carrier frequency, what kind of sound will be heard in our FM radio receiver? So this is the simplified case, of course, right? But you don't want to put here some phi of t for the simplified case, right? So in FM received signal, in the extreme simplified case is that there is no sound, right? And also interference, the simplest case is that it is a single tone with non-zero frequency offset, because frequency offset 0 means nothing. It's too simple, and you remove the essence of the problem. So given that, what will happen? So here, what I suggest is this one. Find the complex envelope of this signal. So what I do is like this. The first term is simply AC e to the j 2 pi FCT, right? Real part of. Second term is real part of what? So AI e to the j 2 pi FC plus FIT. This must be instant. And we have real part operator. So we take AC out. And here are our common factors. So you have AI e to the j 2 pi fit e to the j 2 pi fct. So this is the complex envelope of our received signal, this one, real valued bandpass signal. So this is complex envelope. Now, what do we do? If this is the FM signal, supposedly FM signal, our FM receiver will take what? Will take the derivative of this one and uh, what? And take the complex envelope again. So what do we do? And some of you may say that what's the derivative of real part of something, but there is a simple trick. What we do is that we replace real part of something as 1/2 times this argument times its complex conjugate. So we have a I e to the negative j to, sorry, AI and negative 2 pi fit e to the negative j 2 pi ct. Now we can easily differentiate this one. Then what do we have? So yeah, there are two ways, of course. We differentiate this one first and then find the complex envelope. So let's do that. So we have negative AC 2 pi fc sine 2 pi fct minus AI 2 pi fc plus fi and sine 2 pi fc plus fit, right? This will be easier. So this is real part of 0 plus j AC 2 pi fc e to the j 2 pi fct plus the second term becomes again 0 plus j and this one AI 2 pi fc plus fi and we have this one e to the j 2 pi fit e to the j 2 pi fct. And again, these are common, so you have real part of j, and you have that one, AC 2 pi fc plus AI 2 pi fc plus fi e to the j 2 pi fit, something like this. Am I right? I'm losing confidence. Is it correct? I hope so. Yeah. So this is the derivative, and let's take the envelope. So envelope detector output would be this one. So what is the envelope detector? So we have this cosine and sine, right? So let's take 2 pi out. Yeah. Because scaling doesn't matter, we can put any amplifier or attenuator. So we have AC plus, so AC plus AI, sorry about that, AC FC plus AI FC plus FI cosine 2 pi FIT plus J AI FC plus FI sine 2 pi FIT. So this is the complex envelope. So this complex envelope is J times this one. So let me be careful. So this one is same as that. Now we take the complex envelope. Then what will happen? because we have a real part, after we remove that one imaginary part, we have to have this one squared plus that one squared, and we take the square root to have the output complex envelope. So AC FC plus AI FC plus FI cosine 2 pi by T squared plus AI FC plus FI sine T squared. And this is the output of envelope detector. Got it? And this is actually very confusing. So what kind of simplification is possible? We just consider angle modulated signal first, so that we don't have this differentiator followed by envelope detector to analyze the output of FM. So the authors of textbook just take the complex envelope like this, right? So this complex envelope has real part and it has time varying part. So this is real. So we have some vector of magnitude AC. And here we add something. This is the magnitude and this is phase. So if AI is small, then we have small size vector added here and it rotates with frequency Fi. Got it? If this AI is very, very small, then we have very small perturbation. So of course, there will be no signal because there is no time varying phasor. Got it? But what if we have very big component AI compared to AC? Then relatively this is small, so we have very fast varying phasor. And if that is frequency modulated signal, we have what? If we differentiate that, we have a tone. So we have very large B type of sound. Got it? So here, the authors didn't want to have my complexity of having a differentiator followed by envelope detector in order to explain the result very qualitatively, but very quantitative idea to get the output of the differentiator and differentiator followed by envelope detector, you have to use this type of approach. Got it? Anyway, this simplified model, assuming this general angle modulation, is also very, very useful by using this simple complex vector. So as you see here, this AC is much bigger than, it's bigger than AC, and here AC is bigger than AI. AC is much bigger than AI. In this case, AI is bigger than AC. So you have some extreme cases. So one simplification is AC is much bigger than AI. The other simplification is interference signals amplitude is much bigger than carrier's signal. And actually, we have intermediate cases. And as your intuition says that if this case, weak signal case, interference does not give us any interference. So FM discriminator will give you silence if the signal is silent. But in this, the other extreme, you will see B type signal. And this is in the frequency domain, it looks like this. Suppose this is your carrier frequency, and you are supposed to have your desired signal spectrum like this, assuming single tone. So this is our desired signal. And unfortunately, suppose here is some interference. So this is FC plus FI. Of course, you may have also some other signals, but let's assume that. So here, our signal is no longer zero, no longer MT zero. right? But here m of t equals 0 actually. Here m of t is no longer 0, but single tone. Still simplified case. So we have these tones as you've seen in the simplified analysis. Now we have interference. What will happen? Yeah, almost the same. Yeah. If this is much bigger, then this is silence, then you will see B-type interference. However, this is much stronger, then this signal will be heard and that signal will be ignored. Got it? That's the idea. Now, let's see what's going on in the FM receiver. So in the transmitter, we use pre-emphasis. Pre means before, and D means undo. So this is undo. Okay. So pre-emphasis means that before transmission, you do emphasizing. The emphasis means that you undo the emphasizing. So this occurs in the transmitter, and that occurs in the receiver of the FM radio. Right? And why? Why we do that? And that is related with the differentiator followed by envelope detector type receiver structure. So let's see what happens at the output of the differentiator first. So differentiator is modeled as a linear time invariant system with frequency response j omega. So in the complex baseband, we may view something like this. So this is the amplitude, magnitude response. So magnitude response emphasizes from 0, which is in passband, real passband. You amplify the components away from your center frequency. So here we do the same thing. Suppose this is 0, which corresponds to FC in the real passband, but 0 in baseband. Then here you have negative frequency and you have same thing. So this line is will be effective after your FM radio transmission and reception using differentiator followed by envelope detector. So this derivative operator, if there is no interference, it gives us back our message signal after envelope detection. However, let's just think about the interference only. What happens? From the carrier frequency, so this complex sample, if you have interference that is spaced far enough, but still, if your differentiator or approximate differentiator is amplifying that magnitude, that interference effect at the output of your receiver will be huge. This is this line. So FM receiver without any preparation will hugely emphasize your interference. And this is the amount of offset. So this 0 means actually FC in the real passband. W means FC plus W in the real passband. Got it? So even though your interference is far away from your desired carrier, it may be hugely amplified, and that is not good. So what do we do? Here goes something interesting. Here is so-called de-emphasis filter. So in order to compensate for possible huge amplification of largely deviated signal from the carrier frequency, we have this filter that reduces the gain of the, so combination of this one and that one actually. Combination of these two becomes this one. So actually this de-emphasis filter will look like something like this. Got it? So this added like that will be something like that. Okay, so combination of these two now is this one. Got it? Then what will happen? The interference signal far enough from the center frequency will not be much emphasized now by this combination of de-emphasis filter followed by differentiator. So that is good. Then what is bad? The bad thing is that, as I've shown you already in this example, we not only have the tone, but also have our harmonics uh, that deviates from our carrier frequency if we have single tone, simplified single tone message. So the problem is that this de-emphasizing filter may distort our desired signal. So what do we do? So what we do is that in the transmitter, here goes our pre-emphasis filter. That is bandpass filter, and that pre-emphasizes, so it looks like that, pre-emphasizes our transmitted signal. So that actually is the signal that will be applied to the power amplifier. So the output of our signal here, if we view it as a real value bandpass signal, actually these signals are actually amplified relative to the signals close to the center frequency. But in the receiver, this de-emphasis filter will rectify and equalize the signal as if there was no de-emphasis and pre-emphasis filter. However, for the interference, due to this de-emphasis filter, its effect is not hugely affect the quality after differentiator and envelope detector. That is the idea. So let me repeat. So without, let me just follow this. Without the emphasis filter in the receiver, the FM discriminator, which is mathematically speaking, the differentiator followed by envelope detector, especially differentiator, will hugely amplify interference, even though its frequency deviation is significant from the desired frequency because of the nature of the differentiator's magnitude response. So they put the emphasis filter so that the combination of the emphasis filter followed by differentiator now does not look like this one, but this one, which means that the interference is not much amplified. The problem is that the desired signal also will be de-emphasized. So in the transmitter, we have pre-emphasis filter. So the combination of pre-emphasis and de-emphasis will be equalize the magnitude for the desired signal, so that desired signal passes through this differentiator followed by envelope detector properly. That is the idea. Got it? So pre-emphasis filter will definitely be high pass or high amplifying filter, and the emphasis filter is low pass filter, so that the combination of this combination of the emphasis filter followed by differentiator may suppress the unwanted interference under the desired level. Got it? So here goes the summary. So in the transmitter and receiver, you have pre-emphasis filter. You may do pre-emphasis before the even before FM modulation. So here is the message, and message is pre-amplified. And this is one way, and the other way is that the M of T, FM modulator, and here goes the pre-emphasis filter, bandpass filter, and the transmitter. And same, sorry about that, our amplifier. You have LNA, you have B-emphasis filter, followed by differentiator, envelope detector, something like that. So as you know that most of this pre-emphasizing and FM modulation may be implemented in the baseband. So what they do is that they pre-emphasize the message, not the FM signal, and de-emphasize the output of the discriminator. That is another way. So any implementation is possible, and actually this is more preferred than that one, but this is also possible. And this can be implemented also. Got it? So pre-emphasis and de-emphasis is related to the nature of the differentiator followed by envelope detector type FM discriminator. By the way, in the previous chapter, at the end of previous chapter, I talked about, actually I showed this slide to you and talked about especially the pulse amplitude modulation and little bit about pulse width modulation, pulse position modulation. And I said that I will talk about the other modulations after we learn the angle modulation, but I found that that is not good for to be explained here. So let me just repeat that there are interesting ways to encode analog signal in a semi-digital format. So suppose you have a sinusoidal analog signal, then pulse amplitude modulation is much related to you sample and convert the amplitude to a short pulse with varying amplitude. Pulse width modulation is that you sample and you convert the amplitude as a width, and in pulse position modulation, you sample the analog signal, and depending on its height, you introduce the offset from the periodical epochs. That is the idea. Okay, and also I talked about frequency division multiplexing last time, and I'm not going to repeat. Okay, so here goes the topic about stereophonic or stereo sound FM transmitter and receiver. And let's see this one first. Here, the title is FM stereo broadcasting band. And here, it's 0, but actually this is complex baseband. So actually this becomes FC, and all the numbers must be FC plus these numbers. And also you have the negative frequency. So actually you have something like that one that is flipped again. So here you have around 100 kilohertz, and you have 100 kilohertz. And if you add up, you have 0.2 megahertz. And I told you in the beginning of last class meeting that from 88.0 megahertz to 108.0 megahertz, the US and Republic of Korea assigns FM radio broadcasting frequency channels. And each channel has channel width 0.2 megahertz. That's why all the stations has the call sign like something like this for KBS FM. And the next one is around 0.2 kilohertz separated, which means that if this is the carrier, then the bandwidth is total 0.2 megahertz, which means 200 kilohertz. So from the carrier, you have around 100 kilohertz right side and 100 kilohertz left side, so you have 200 kilohertz band. Now, interesting thing is this one. Suppose you have a stereo sound, original music. So you have one left side signal and right side signal. And you may say that, okay, this right side signal and left side signal is FM modulated and transmitted. That's not true. People have been much clever. So what they have done is that they have sum and difference of the signals. And this sum of the right and left is, if you follow this one, is FM modulated. So actually, from carrier, you have tone and some harmonics if the sum is a single tone. Got it? And here goes pilot tone, that is twice frequency multiplied and just FM modulated. So you have a tone signal, FM modulated, so you have again pilot tone. Got it? So you have two pilot tones. And here goes something interesting. So you have difference of the signal, and that is also FM modulated with here offset. So sorry, before when I talk about pilot, pilot is past and this way. So you have right and left shifted signals from the carrier by twice of 19. So you have 19 and 38. So here goes the again, possibly if there is tone, then you have this signal. Got it? So why do we do that? Why do we do that? So this signal, the right plus left is put together around the carrier. So if the signal passes through some frequency selective channel, so which means that the before transmitter and receiver, we have, for example, real valued bandpass filter, whose frequency characteristic is frequency selective, which means that its magnitude response varies in the frequency domain. But since these two bands are close together, the change is not much. So we can easily recover very accurately the sum signal from the received signal. The problem is this left minus right. If the channel is flat enough, you may extract the signal correctly. In that case, in the receiver, what they do is that uh, they add these two to find the left signal. They subtract these two to find the right signal, right? L plus R plus minus L minus R becomes 2L or 2R, right? So this way. And if the distortion is very large, then this difference signal may be attenuated. So, for example, your sum signal is okay, but you have, for example, half of left minus right. Then what will happen? You have 2/3 left, right? And you have 1/3 right, and you have 2/3 right and 1/3 left on your right and left. So even though your stereo sound is distorted, your balance is not much distorted. See that still on the left side, your left signal is loud, and on your right side, right signal is loud, and their gains are the same. The problem is that if you just send right signal and left signal differently and they experience different gain, then your, for example, piano sounds much louder than your violin, which was supposed to be of same magnitude. So the early FM stereo broadcasting, they have devised this clever idea. So they sum the left and right signal and modulate. And they subtract left and right signal and FM modulate and then transmit. That is the idea. Got it? Okay, here goes the quadrature multiplexing. And what is the main idea? So whenever we do radio broadcasting or radio transmission, we have this structure, right? So here goes some signal that can be modeled as real valued bandpass signal. So it is always something like this. It can be written in this form. Any real valued bandpass signal can be written in this form, which means you have in phase component and you have quadrature phase or quadrature, simply quadrature component. What does this mean? Any real valued bandpass signal can be generated by first generating real baseband signal, another real baseband signal, and multiply sine and negative, cosine and negative sine. Here goes local oscillator, and then sum up and power amplify and transmit. This type of transmitter is called IQ modulator. Some people say product modulator. Some people say quadrature modulator. And they are based on this idea. Any real valued bandpass signal can be written as the sum of real baseband times cosine minus real baseband times sine. So here goes real baseband, cosine, real baseband, negative sine, and they are summed up. So actually, this is that part, right? This is the transmitter part. And what about the receiver part? In the receiver part, what you can do is this. Suppose here goes your received signal. And this is also real valued bandpass signal. And what you do is this one. Let me explain a little bit lengthy. So your received signal is again a real valued bandpass signal. So you have in phase component, yi of t cosine, and the quadrature component, yq, negative yq of t sine. So this is your received signal. And what do you want to do? Your receiver wants to possibly extract the complex envelope or extract the real part and the imaginary part of your complex envelope. And let's consider taking out this one. And in order to do that, what people have found is an idea like this one. So what you do is that this is your real valued bandpass signal written in this form. You multiply e to the j 2 pi fct and low pass filter. And let's see what happens here. So first, you have low pass filter and what? What is y of t? 1/2 this one. So let me say this is yc of t. So yc of t e to the j 2 pi fct plus yc conjugate of t e to the negative j 2 pi fct. So this square corresponds to the same thing. Y of t is real part of y complex envelope e to the j 2 pi c. Now you have a demodulating complex sinusoidal signal, right? And this low pass filter passes on only the baseband. Let's see. The product of these two becomes baseband signal. So after low pass filtering, you have what? 1/2 yc of t. What about this one? This yc conjugate of t e to the negative 2 pi f 2 fct does not pass the low pass filter. So you have, interestingly, the complex envelope. The problem is that this is real bandpass, and this is complex. So there is no circuit that can handle, no analog circuit that can handle uh, complex signal. So what you do is that you think about the real in real out system. So what you do is something like this. So you multiply. So let's see, how do I say that? Um, yeah. So what you do is that we consider multiplying both sides. Okay, so let's see this one. Let's divide this one. So this is y of t cosine 2 pi fct minus j y of t sine 2 pi fct, right? Right? See that? This argument of the low-pass filter is simply this one. If you use Euler's identity applied to e to the negative cosine 2 pi fct, right? Now, we have low-pass filter, low-pass filter. So, it can be written as low-pass filtered version of the received signal times cosine 2 pi fct and minus j low-pass filter y of 2, y of t sine 2 pi fct, right? And since this is yi of t plus j yq of t, what happens? This one becomes 1/2 of yi of t, and that one becomes, let me see, is it correct? Just a second. Let me see, is it okay? Yeah, I think we have to multiply. Yeah, so this negative, yeah, this one becomes 1/2 yq of t. So in order to extract yi of t, so yi of t equals 2 times low pass filtered version of received bandpass signal cosine. And your imaginary part of complex envelope is negative, sorry, 2 times low pass filter y of t times negative sine 2 pi fct. That's why we have this. By the way, see that I modified our textbook's figure. I put negative sign here and negative sign here. Our textbook shows positive sign. That is not precise. As you see, we have a negative sign that is related to that one. And we have negative sign here that is related to that one. Got it? So precisely speaking, you have to use cosine and negative sign in the quadrature or IQ modulator. And you have to use 2 sign. And if you use 2 sign, what happens? If you have 2 here, then this disappears. And you have 2 here, that disappears. So 2 goes there and negative 2 goes there. Got it? So y of t times 2 cosine gives you the real part, right? And received signal y of t times negative 2 sine low pass filtered will give you quadrature. Got it? So let me emphasize again. We need to change our textbook, negative and negative. Got it? So what does this mean? Suppose in the simplified case that our transmitted signal is the same as our received signal. Then what will happen? This one will be same as M1. That one will be same as M2. So actually, even if M1 and M2 have different signal, but have same bandwidth B, for example, this is left side and this is right side for stereo communication, then actually in the passband, is a real baseband. In the passband, we have these signals taking up to be in real passband bandwidth, even though we transmit stereo sound. And you remember in our DSP, SC, or AM signal, even though we transmit a single one, left or right, we spend our 2B bandwidth in passband. But it seems that, according to the theory, we don't need to wait the bandwidth. So in DSP-SC, in order to save the bandwidth, we devised SSB, but SSB required too much, so we modified and trade off to have VSB, vestigial sideband. But it seems that, mathematically speaking, we don't need that, right? We transmit two signals, and we may save the bandwidth, actually. And this type of modulation is called quadrature modulation, or sometimes analog quadrature amplitude modulation, because in-phase and quadrature components are both used for transmission. But in practice, this type of modulation is rarely used for analog modulation, because in analog modulation, the receiver host, otherwise, complexity in the receiver is very, very important, but it's very hard to have phase coherence in the receiver with the received signal without increasing the complexity of the receiver. So only in digital communications, this quadrature multiplexing or quadrature amplitude modulation is very popular. So you will learn a lot in the next course, the Introduction to Digital Communications, where you will see quadrature amplitude modulation. By the way, see this one. A real valued bandpass signal has complex baseband signal equivalent to it, right? So that's why in communication, digital communications, we just said, here goes complex valued signal to be transmitted. Complex baseband, actually. Got it? Why? Because a real valued bandpass signal has its equivalent complex baseband signal. So we put that complex baseband signal here, and then we upconvert and take the real part to have real valued bandpass signal. Got it? Now, I've spent already 1 hour and 15 minutes, but let me talk about the last topic. So the last topic is about multipath channel and why amplitude distortion happens. So multipath channel is a radio channel that has multipath. So what does that mean? Suppose here is your transmitter antenna and here is your receiver antenna. And so far, we assume that our radio wave just propagates as if it propagates through free space. However, in reality, we may have some reflector here. So the signal is reflected here and may arrive in the receiver. So if we approximate it as if we had in geometric optics, 기하, 광학 in Korean, we may assume that we have a single straight line path, line of sight path, and one reflected path. So how many paths do we have here? This is the line of sight path. This is non-line of sight path. So we have, in this case, two paths. If there is no this reflected path, we have only line of sight path. In that case, we have single path. And this is our emphasis so far. Of course, even though we have one path, of course, we have attenuation and delay, but that are all ignored. So after one, there are 2 and 3 and 4 and many. And from 2, we have come multipath channel. So this case is called single path channel. And single path, of course, may consist of single reflected one, but special case is line of sight path only existent. Okay. So now, what happens? You have multiple paths in radio propagation, and as you see here, the path length is different. So suppose the signal component of line of sight path is attenuated version of the transmitted signal. Now, what about this single bounced path? It would have different gain and different delay, right? And now, what will happen if we have this multipath? And you may say that it's hard to do anything, but actually you can do a lot. Suppose your signal is real valued bandpass signal having complex envelope XC. Now, your received signal is G1 of X t minus tau 1 plus G2 of X t minus tau 2. And as I've given you a hint, let's find out the complex envelope of this real valued bandpass signal. And you can easily show that you have G1 XC t minus tau 1 e to the negative j 2 pi fc tau 1 plus G2 XC t minus tau 2 e to the negative j 2 pi fc tau 2. And this becomes the complex envelope. And then you have carrier. So finding this part must be also instant, right? And so what? This simple one is become more complicated, but here goes something interesting. Suppose we have, even though tau 1, tau 2 different, they are very close, so that we may say xc of t minus tau 1 is almost same as xc t minus tau 2. Now, that's okay, right? For example, xc looks like that. Xc of t minus tau 1. And if tau 1 minus tau 2 is relatively smaller than this one. Okay, so this is xc t minus tau 2. We may say that they are almost the same, right? So under this assumption, we have what? We have the received signal is approximately G1 e to the negative j 2 pi fc tau 1. Sorry. Let me factor out. So we have G1 plus G2 e to the negative j 2 pi fc tau 2, so plus tau 1 minus tau 2 e to the negative j 2 pi fc tau 1 e to the j 2 pi fct. We can write this way. Oh, sorry, x. Xc t minus tau 1 e to the negative j 2 pi fc tau 1 e to the j 2 pi fct. Got it? So this becomes the complex envelope. Got it? And let's see, what is this one? This is constant, right? We have some phase offset to this complex delayed version of our transmitted signal as complex envelope. What about that one? And you may say that tau 1 equals approximately equal to tau 2. So this is 0 and this is 1. And so we have G1 plus G2. But be careful. Even though tau 1 is approximately equal to tau 2, this FC may be very large relative to this one. So this product may not be ignorable, FC tau 1 minus tau 2 to pi may not be ignorable. It may be much larger than 0, of course, much larger than 0. In the case, we have phase hugely different from G1. Got it? So in complex domain, if this is G1, G2 may be that direction. Got it? And something interesting happens. Suppose this reflector moves that direction. What will happen? This line of sight path will be fixed, right? However, the path length of this non-line of sight path will increase. And that is related to the increase in tau 2. Of course, still we assume tau 1 is approximately same as tau 2. So we invoke this assumption. So here, this is okay. However, now, this is now time varying because tau 2 increases. Then what will happen? Sometimes this phasor and that phasor may destructively superimpose or constructively superimpose. So what will happen is that due to this something moving in the propagation medium, sometimes reflector, sometimes even the transmitter itself may move or receiver may move. If something's moving in the channel, and if there are more than one path, then you may have time varying amplitude distortion. See that? Suppose this is FM signal. Now this is time varying. You have then amplitude distortion. That's why in radio communication, you may have this effect. And of course, this reflector may be something like bus moving around you, or sometimes it could be ionic sphere, 이온층, that is time varying. This whose thickness or height may vary. Right? So that kind of something moving, something in motion in the channel, radio channel, and if there are more than one path, then you may have amplitude distortion. That is very interesting. That's why we have AM signal that is not that of high quality in radio broadcasting. So message is conveyed by the amplitude of the carrier, but there is amplitude distortion. Then your signal is distorted. And in FM, your message is not in amplitude, but still there is amplitude distortion. So what do? We just remove the distortion at the variation in, or reduce or suppress the variation in amplitude by using bandpass limiter. And that bandpass limiter does not significantly affect the message signal because this equalized amplitude does not convey our message. And then bandpass filter may almost introduce no distortion in zero crossing points and amplitude. And then our FM discriminator will give us the signal, which is, for example, pre-emphasized one. So we put the emphasis filter so that we can suppress the strong interfering adjacent signal. Okay, so that's for all today. See you on Wednesday.